Welcome to part 4 of this video playlist about the best methods for converting aliphatic alcohols into alkyl fluorides. This presentation is about the use of sulfonyl fluorides as deoxyfluorinating reagents. These are less reactive than aminosulfur trifluorides or fluoroalkylamines, but more reactive and versatile than anhydrous hydrogen fluoride. Although the two-step strategy of converting an alcohol into sulfonate followed by SN2 displacement with fluoride has been known for many years, the one-pot procedure using a sulfonyl fluoride has only recently emerged as a viable deoxyfluorinating protocol. Sulfonyl fluorides are generally less reactive but more selective sulfonylating reagents than sulfonyl chlorides. And in the absence of catalysts, the first step of this reaction, namely sulfonate formation, can be rather slow. Then, as would be expected from the mechanism of this reaction, the rate of the second step will generally increase if the sulfonate chosen is a good leaving group. Because SN2 reactions with fluoride do not proceed smoothly, and because SN2 reactions are accelerated strongly by increasing the concentration of reactants, the results of this reaction can often be improved by adding external fluoride, for instance tetrabutylammonium fluoride or potassium fluoride. It has also been observed that bases such as DBU lead to higher yields, what may be due to the better solubility of amidinium fluorides than alkali fluorides in most organic solvents. Bases may also be required to increase the nucleophilicity of the alcohol and thereby the rate of sulfonate formation. The most common sulfonyl fluorides used for deoxyfluorinations include perfluorobutane sulfonyl fluoride, which boils at 64 degrees Celsius, 2-pyridine sulfonyl fluoride, which is a solid and melts at 29 degrees Celsius, and for phenols, sulfuryl fluoride, which is a gas with a boiling point of -55 degrees Celsius. The main advantages of sulfonyl fluorides as deoxyfluorinating reagents are the simplicity of the handling and the high yields that can be attained. Sulfuryl fluoride, which is an inexpensive fumigant, has only been used to deoxyfluorinate phenols, but may be suitable for aliphatic alcohols too. Main disadvantages include the high price of fluoroalkane sulfonyl fluorides and the fact that stoichiometric amounts of sulfonic acids are produced as waste. In this example, a primary phenetyl alcohol was converted into a fluoride by treatment with pyridine sulfonyl fluoride and an excess of a guanidine. 8% of a styrene was formed as byproduct. This example is similar to the previous one. A secondary alcohol was converted into the fluoride by treatment with a slight excess of pyridine sulfonyl fluoride and 2 equivalents of DBU at room temperature. As byproduct, 4% of a mixture of olefins was obtained. In this example, treatment of a hydroxyproline derivative with an excess of perfluorobutane sulfonyl fluoride, a fluorosilane and a tertiary amine yielded the corresponding fluoride with inversion of configuration. The fluorosilane was meant to be a non-basic source of fluoride to prevent the formation of olefins. In this optimized example, the target was a cis-1,2-difluorocyclopentane, which was obtained in good yield upon treatment of a trans-2-fluorocyclopentanol with perfluorobutane sulfonyl fluoride and triethylamine. The required alcohol was prepared by ring opening of an epoxide with HF and was used without isolation. 2 aminoethanols do not readily eliminate water because the resulting enamines are energy-rich and more reactive than normal olefins. Nevertheless, in this example, a high yield of the expected alkyl fluoride was obtained from a substituted N-hydroxyethyl-imidazole along with 9% of the olefin. Anyway, all these examples show that these reactions proceed quite well with both primary and secondary alcohols, usually at room temperature and with only a slight excess of reagents. What are the typical side reactions of sulfonyl fluoride-mediated deoxyfluorinations? Because SN2 displacements with fluoride are often sluggish, the reaction may stop at the sulfonate stage. and one byproduct to be expected is the intermediate sulfonic acid ester. If a perfluoroalkane sulfonyl fluoride was used, these sulfonates may hydrolyze to the starting alcohol during an aqueous workup or undergo elimination if an excess of base was used. It should also be kept in mind that guanidines or amidines such as DBU can be alkylated at nitrogen with alkyl sulfonates, and a large excess of base should therefore be avoided. Because fluoride is a poor nucleophile, other nucleophiles may compete with fluoride for the electrophile. These include the other halides, pseudohalides such as thiocyanate, and neutral nucleophiles such as pyridines, amides or ureas. As illustrated by the examples on the previous slides, beta elimination is also a common side reaction. A large excess of base and high reaction temperatures may increase the yield of olefins. Then, other oxygen-containing functional groups, such as aldehydes or ketones, may also be deoxyfluorinated. Because most sulfonyl fluorides presented above are expensive, a two-step procedure should also be considered, in which the alcohol is first converted into mesylate and then into the fluoride by nucleophilic substitution. Mesylate formation is fast, high-yielding and easy to perform, and the substitution with fluoride seems to proceed well in tertiary alcohols as a solvent, as shown here. Here are some further examples and review articles. In addition to the use of hydrogen fluoride, aminosulfur trifluorides, fluoroalkylamines and sulfonyl fluorides, a number of other strategies have been reported for converting alcohols into fluorides. Although none of them is widely used, further optimization or the use of catalysts or fluoride-containing additives may render some of these strategies more useful. These will be presented in the next video.